Welcome to this training video on the laboratory DN test procedure, which is an essential aspect of the DCP-DN Pavement Design Method. The production of the video was supported by UK aid through the Research for Community Access Partnership ReCAP. The video was produced by the South African Council for Scientific and Industrial Research, CSIR, as part of the production team for Infra-Africa Consultants, Botswana. The video forms part of a suite of tools aimed at facilitating the cost-effective and environmentally optimized design of low-volume roads in both tropical and subtropical regions of the world. By way of background, UK aid, through the Foreign, Commonwealth and Development Office, has been at the forefront of supporting research in the design of low-volume roads in Africa and Asia to improve access to infrastructure and transport services. Such access is, of course, essential to economic growth and service delivery in all developing countries where low-volume roads provide the main form of transport in rural areas. ReCAP has been working closely with partner governments in Africa and Asia and has produced technical documentation that reflects best practice, including a manual on pavement design of low-volume roads using the DCP-DN method. As part of the suite of tools on the use of the DCP-DN design method, this video on the laboratory DN test procedure has been developed to assist engineers in the design of low-volume roads based on the DCP-DN Pavement Design Method. For any pavement design method, standard material tests such as adiabatic limits, grading, and strength based on the CBR-ODN test are used for assessing the suitability of subgrade and borrow pit materials for incorporation in the pavement structure. As many designers would be aware, the DCP test has traditionally been used for assessing the strength of in-situ subgrade materials. However, in the DCP-DN pavement design method, this test is also used to assess the strength of subgrade and borrow pit materials by way of the laboratory DN test. The laboratory DN test is central to the DCP-DN design method and replaces the more traditional CBR test that is used in other design methods. Thus, the main purpose of the video is to guide designers in all the procedures required to undertake the laboratory DN test in a consistent and correct manner. The objective of the video is to ensure that the designer is able to carry out the laboratory DN test strictly in accordance with the procedures described in the DCP-DN Pavement Design Manual so that reliable test results are obtained for input into the pavement design process for low-volume roads. The video covers in a sequential manner all the procedures required to undertake the laboratory DN test, starting with the sampling of materials from existing roads and borrow pits, through to the manner of undertaking laboratory compaction and DN testing, to analyzing, recording, and interpreting the laboratory DN test results for pavement design purposes.
In the first section, we look at the materials evaluation framework, the aim of which is to identify materials that are potentially suitable for use in the low-volume roads pavements. The objective of Stage 1 is to screen out and exclude from further testing materials that are clearly unsuitable for use in the pavements. This will typically include problem soils with deleterious properties such as excessive swell, salinity, erodibility, and collapse potential. The screening is based on the results of traditional classification, grading, and other appropriate tests, and engineering judgment applied for the selection of materials for specific use in the subgrade of pavement layers, always bearing in mind the preference for using local materials. Finally, the upper and lower limits for the grading modulus of the materials will exclude overly fine and overly coarse materials, and will ensure that only materials that are deemed suitable for incorporation in the pavements will be passed on for compaction and laboratory DN testing. Stage 2 comprises the standard compaction test to determine the maximum dry density and the optimum moisture content of the materials, and the laboratory DN test, which will determine if the materials are strong enough for use in the respective pavement layers as specified by the DCP-DN design catalog. In stage 3, a risk assessment is carried out by analyzing the DN density and moisture content relationship, which shows how the strength of the material varies with compacted density and changes in the operational environment, which may influence the moisture content in the various pavement layers. The main focus of this video is the laboratory DN test during stage 2, but we will also go through the various activities and tests that are required before materials can be subjected to the laboratory DN test. The full laboratory DN test program involves testing materials at 3 different moisture contents and 3 compactive efforts, as shown in this matrix. For each combination of compactive effort and moisture condition, a minimum of 3 samples should be tested in order to obtain reliable results. So why do we need to carry out at least 3 tests for each combination of compactive effort and moisture content? All laboratory tests have an inherent coefficient of variation, which means that there will always be a variation in the test results. And these variations will occur even if the tests are carried out in accordance with the required procedures. So we carry out a laboratory DN test, which gives us a lab DN value of 9 as shown in this diagram. But this test alone will not help us in determining the representative DN value for that material. So we have to carry out a second test to check on the result of the first test. And this test gives us a DN value of 4. The difference in the test results between the 2 tests can be in part because of the coefficient of variation, but it's also possible that for either of the 2 tests, an operator error has introduced a larger variation in the results of the 2 tests. So based on these 2 tests, we simply cannot tell which of these test results is the most representative for that material. So we have to carry out a third test, as shown in this diagram. And test number 3 gives a result that is fairly close to test number 2. And it's apparent that we may have more confidence in combining the results of test number 2 and 3 and regard test number 1 as not being a valid test result for that material. If we were to use the average of all 3 tests, we would get a DN value of 6. Whereas if we disregard test number 1 and use the average of test number 2 and 3, we will get a DN value of 4.5. The result of test number 1 is outside the expected range in the variation of the test results, and it seems reasonable to assume that the result for test number 1 was caused by some sort of operator error. We therefore have more confidence in test number 2 and 3, and we can use the average of those 2 test results as a representative DN value for that material. The laboratory DN test must be carried out with the highest degree of accuracy, as indeed must all the preceding activities and tests. In practice, a reduced testing program may be sufficient for attaining the required information for design. As explained in the DCP-DN Pavement Design Manual, You may reduce the testing to two different moisture conditions, say at OMC and soaked, if you are in a wet climatic zone, and at 0.75 OMC and OMC, if you are in a dry climatic zone. The selection of the tests to carry out will also depend on the microclimate for the sections under design. The following provides an overview of all the material evaluation activities, from sampling materials in the field through to the analysis of the laboratory DN test data. The first section deals with appropriate procedures for sampling materials from uniform sections on the road or from borrow pit stockpiles. The next section will deal with the preparation of the materials in the laboratory to dry, mix and quarter the materials to ensure that we have identical samples for testing. The next section deals with the preparation of the samples for compaction using either of the two methods that are described in the DCP Pavement Design Manual, the scalping method or the crushing method. Then we go on to discuss the compaction testing to determine the maximum dry density and OMC of the material, and also to determine the field moisture content and the ratio of the field moisture content to the OMC of the material, which is essential if you are going to use the percentiles option for design. Next, we are going through the compaction procedures in the laboratory, how to mix materials, and how to compact specimens. And the video will show machine compaction and manual compaction, which is still used in many laboratories. Then we go on to discuss the preparation of the specimens for the laboratory DN testing, which is followed by the laboratory DN testing itself. And lastly, we will discuss how to analyze and interpret the laboratory DN test results. In this section, we'll deal with the material sampling and the preparation of the materials in the laboratory. So how to sample materials from existing roads? You have to excavate 3 test pits from each uniform section and obtain 3 bulk samples. If there are different strata in the subgrade, you have to sample each stratum separately. You must take and seal the samples for moisture content determination. And you must label the samples properly, including the chainage and materials description, sampling date and depth, etc. The recommended sample sizes for compaction tests are as follows. Compaction using the CBR mold, approximately 80 kg. Compaction using the 1 liter mold, approximately 25 kg. And compaction using the vibrating hammer, approximately 80 kg as well. How to sample materials from borrow pit stockpiles. You have to obtain samples at different locations and at various levels of the stockpile. Record the borrow pit details, including the chainage, material description and sampling date. The recommended DN testing frequency for pavement materials are as follows. For base material, a DN test should be carried out at least for each 5,000 cubic meters of material. For sub-base materials, this can be reduced to 1 test per each 10,000 cubic meters of material. In the following, we'll go through the general procedures for preparing materials once you have brought them into the laboratory. You first have to register materials, and the material indexing system should include a job reference and sample number. You then have to air dry the materials. It's very seldom that the materials you're bringing into the lab are bone dry, so you have to make sure that all lumps containing clay and silt are properly broken down. Then you have to thoroughly mix the materials to obtain one bulk sample. But you must make sure that you're not mixing materials from different strata on the road. You then quarter the samples using the riffler to obtain representative samples. And lastly, you store the samples in bags for future testing. The preparation of samples for compaction should follow the procedures described in the DCP-DN Pavement Design Manual. The first method is the scalping method, which applies to materials that have 30% or more by weight retained on the 20 mm sieve. You first remove the material passing the 37.5 mm sieve and which is retained on the 20 mm sieve. You lightly crush the aggregates by means of a steel tamper so that all that material passes the 20 mm sieve. Then you recombine a portion of the crushed material representing 30% by mass of the original sample with the rest of the original sample. You thoroughly mix the materials and you split the materials into subsamples, approximately 7 kg for each, for compaction at different moisture contents and compactive efforts. The second method is the crushing method, which applies to materials that have 30% or less by weight retained on the 20 mm sieve. Again, you screed the sample on the 20 mm sieve. You lightly crush the material by means of a steel tamper so that all of the material passes the 20 mm sieve. Then you recombine the crushed material with the rest of the original sample, thoroughly mix it, and again you split the materials into subsamples of approximately 7 kg for compaction at different moisture contents and compactive efforts. In the following section, we will deal with the compaction and laboratory DN testing. There are two main laboratory compaction options: machine compaction and hand compaction. Modern laboratories these days tend to use the machine compaction method, which produces more consistent results. However, many laboratories in Africa and Asia still use hand compaction due to non-availability of machine compaction equipment. To obtain reliable laboratory test results, it is important that the laboratory equipment is checked or calibrated regularly. You should check and keep a register of the mass and volumes of all the compaction molds. And tampers must be replaced when the heads are worn out, as shown on the picture to the right. Electronic balances can be checked for accuracy using standard block weights, and the oven temperature can be checked using a thermometer. If the electronic balance or the oven is not working properly, they must be sent to a qualified workshop for repair. In general, these items should be calibrated at least once per year. Before you carry out a compaction test, you should determine the field moisture content of the moisture samples that you have taken from the uniform sections. The compaction test is the standard compaction test used to determine the maximum dry density and optimum moisture content at heavy compaction effort. And you must follow your national standard when carrying out these tests. Once you have carried out the compaction test, you are then able to determine the relative moisture content of the in situ layers, i.e. the FMC over OMC ratio. As said before, this ratio is crucial if you want to use the percentiles option for design. All samples for the laboratory DN test must be prepared at OMC before compaction. First, you weigh and transfer the sample into a mixing basin. Then you weigh the required amount of water, which you can determine based on the OMC of the material. Then you transfer that water into the mixing basin and you thoroughly mix it by hand. Then you let the material condition in a mixing tray for about 30 minutes. In this video, the machine compaction procedure is demonstrated, but machine and hand compaction procedures are both the same, except for the equipment that is used for compaction. You first weigh the mold, then you assemble the mold and the base plate and secure the assembly on the compaction block. You place the material into the mold. You set the tamper to the required number of blows, and you compact the material in layers. Then you check the level of the material after compacting each layer. When you finish the compaction, you remove the collar and you level the top of the compacted sample using a straight edge. Then you remove the mold containing the compacted sample from the compaction assembly and record the weight. From the mixing tray, you take a sample for laboratory moisture content determination. And you seal that moisture sample in an airtight container and record the weight. And you over-dry the moisture content sample and record the weight. Then you analyze the result to determine the dry density and the moisture content of the sample that you have just compacted. When all specimens have been compacted, they must be prepared for the laboratory DN testing. The specimens must first be allowed to equilibrate to dissipate pore water pressure generated through the compaction procedure. The recommended periods for equilibration are as follows. Those that are going to be tested in a soaked condition must be soaked for 4 days. Those that are going to be tested at OMC must be sealed in plastic bags for 7 days for pedogenic materials or 4 days for non-pedogenic materials. Those that are going to be tested at 0.75 or OMC must be air dried if it's pedogenic materials, or oven dried at a maximum of 50 degrees Celsius for non-pedogenic materials. Calculate the target mass of the sample and the mold for when the moisture content of the sample has reached approximately 0.75 or OMC, and check the weight of the molds regularly. After reaching approximately 0.75 or OMC, seal the specimens in plastic bags for 7 days for pedogenic materials or 4 days for non-pedogenic materials. And lastly, weigh the samples to determine the exact moisture content.
The following part of the laboratory DN test procedure shows, first, how to assemble the DCP device. Second, how to perform the DN test. And third, how to analyze the laboratory DN test data using recap raw volume rods DCP software. The first section shows how to assemble the DCP device. Let me start by introducing the main components of the DCP device. This is the top or upper rod. In this case, it is connected with the handle. This is the hammer. The standard, it should be 8 kilograms. This is the bottom rod. This is the measuring ruler. This is the anvil. This is the guard. And this is the cone. In order to assemble the DCP, insert the hammer into the top rod. The next step is connect the anvil to the top rod. Screw the bottom rod into the anvil. Connect the measuring ruler through the anvil. Insert the guide into the bottom rod and the ruler. Screw the cone. It is important to emphasize that 60-degree cone should be used during the testing. Some countries make use of 30-degree cone. Screw the nut or the foot to the measuring ruler. Check the condition of the cone to ensure that it is sharp. Before doing any testing, check the condition of the cone and ensure that it is sharp and not rough like this one here. After assembling all the main DCP components, this is the final DCP assembly. Before starting the test, you need to prepare a form like this one, where you're going to record the DN test data. Alternatively, you can bring a laptop to the laboratory and record the data directly into the recap raw volume rods DCP software. This is how to secure the sample. Place the CBR mold on top of a base plate. Secure the assembly properly to ensure that the mold remain intact during the testing. The following is how to measure the sample height. You first need to measure the height of the mold from outside, and then you measure from the top of the mold to the sample inside. Then you subtract the inside measurement from the outside measurement to obtain the sample height. The sample height measurement will enable you to stop the test before the tip of the cone hits the base plate. You will also need the height of the sample during the analysis of the laboratory DN test data. Position the DCP cone in the middle of the sample. Hit slightly into the sample. The test should start with the upper portion of the shoulder of the cone flush with the surface of the layer being tested. Position standard annular weight on top of the sample. Use empty upside down CBR mold to support the measuring ruler. After supporting the measuring ruler, you need to take the initial reading. The initial reading, together with the sample height, will enable you to determine when to stop the test before the tip of the cone hits the base plate. For example, in this case here, the initial reading is 50 millimeter. The measured sample height is 120 millimeter. So 50 millimeter plus 120 gives you 170 millimeter. That means when penetrating the sample, you need to make sure that you stop the test before you get to a reading of 170 millimeter. It is recommended that you stop the test within 10 millimeter before getting to the end of the sample. In this case, you will need to stop the test when the reading is at 160 millimeter. It is important to emphasize that samples for the laboratory DN testing should be compacted using 3 compactive efforts, which are light, intermediate, and heavy. The samples should be conditioned at 3 moisture contents, which are 4 days soaked, optimal moisture content, and 75% of optimal moisture content. For each combination of compactive effort and the moisture condition, at least 3 samples should be tested. For this demonstration here, we are using a sample that was compacted using heavy compactive effort and conditioned at optimal moisture content. Throughout the test, you need to make sure that the DCP equipment is held vertically straight. You also need to check and ensure that the top rod, the bottom rod, as well as the measuring ruler are straight and not bent. When doing the test, you must ensure that you lift the hammer all the way up to the bottom of the handle and release it freely. The required dropping height is 575 millimeter. 1. Okay, what's the reading? Okay, for laboratory DN test, you need to make sure that you make use of variable blows. At this point in time, we have already penetrated to 150 millimeter. Our target, the maximum that we can penetrate, is 170 millimeter. That will ensure that the tip of the cone does not hit the base plate. That means from now, we will start reducing the number of blows to ensure that the tip of the cone does not hit the base plate. To be conservative, we will target to stop the test 10 millimeter before we get to 170. After completing penetrating the sample, remove the annular weight. You need to hit very slightly, while supporting the mold. After driving out the DCP equipment, the last step, you need to take moisture sample. In order to do that, you must first remove the material on top of the sample, following which you take a moisture sample from the middle part of the specimen. Okay. After completing the laboratory DN test, the next step is to analyze the data using Recap Raw Volume Rod DCP software. The first step, you need to create a project. To do that, double-click on the software icon, then select Create a New Project, select Laboratory, and click OK. Then you enter the job reference. In this case is JR001. You must specify the date for the project, and then specify the project file name, and then you click Save. Click OK again. Let's now quickly explore the various menu options, which are essentially similar to any software package which you may have used before. The first one, we have got this one here, Insert. It allows you to insert the new mold. Second, Analysis, which is only activated after you have entered the laboratory DN data. System allows you to set the laboratory report options. We recommend that you select all the options that are available here, and they are usually pre-selected. Then you can also explore on the Help menu, where you can get assistance on any topic about the software. Let's now create a new mold so that we can proceed to enter the laboratory DN data. As I indicated before, there are two options. You can either use this Insert New Mold, or you can use this icon here. This icon allows you to insert a new mold. Once you click that, you need to specify the sample number as well as the mold number. Then you click OK. Before you proceed, you need to provide some details here, whereby you must make a selection whether the material that you tested came from a test pit or came from a stockpile. If the material came from a test pit, you then need to specify the test pit number as well as the layer depths. You need to specify the lower boundary as well as the upper boundary. If the material came from a stockpile, you will need to provide details of the stockpile as well as the stockpile number and the location on the stockpile where the material was sampled. For this demo here, the material came from test pit, hence we need to specify the test pit number. We also need to specify the lower boundary, which is the 300 in this case, and you also need to specify upper boundary, which is 150 millimeter. Then you click OK. After you have done that, you need to provide some details here about the test before you proceed. First one being the survey date. You need to specify the survey date. After you have done that, you then need to enter the sample depth. For this case, the sample depth was 120 millimeter. And then there's this icon here. If you click on the icon, it will give you an explanation in terms of how do we measure the sample depth. The next step, you need to always ensure that for laboratory DN testing, variable blows is always pre-selected, and it is recommended that you leave that pre-selected as it is here. Then after you have done so, you need to select or specify the design DN. You click here. After you click there, you will see that on the left hand side there is design DN values for paved roads, and there are about 5 TLCs, traffic load classes, where you can select depending on your specific design situation. On the right hand side, there is design DN for unpaved roads, where it is specified in terms of heavy vehicles per day, and there are about 4 classes. Another thing to take a note here is for the paved road, the traffic class is specified in terms of MISA, where we have a TLC 0.03 all the way to TLC 1.0. 0. You also need to take cognizance that these values here are from these standard design catalogs, but the user has got also an option to use a user-defined DN value. Now let's say for this example that I'm going to demonstrate here, we tested a base material and the TLC that we're designing for is this one here. So we will need to specify that DN value, which is 6.2, and then you click OK. After you have specified the design DN value, the next step, you need to select the compactive effort, where there are 3 options: heavy, intermediate, and light. For this specimen here, the tests were compacted using heavy. And then you need to specify the optimum moisture content of the material, which is 7.5. And lastly, you have to select the moisture condition at which the sample was conditioned. In this case here, it was optimum moisture content. Once you have completed that, the next step is to enter the DN test data. You need to select this DCP reading screen here, and this is where you are going to enter the data. Now let's quickly demonstrate how to enter the test data. The first one, you need to key in the first data that correspond to a 0 blow, which in this case here is 50. Then next you enter 2 blows, which corresponded to 65 millimeter. Continue. 3 blows, 80, another 3, 90, 3 again, 100, 4, 115, 4 again, 125, 5, 140, 3, 150, 2, 155, and then when you get towards the end, you can see the number of blows need to be reduced in order to avoid the tip of the cone to hit the base plate. Okay, when you get towards the end, you need to click Insert New Mold, and you must select Extrapolate using the last 2 reading depths. Then you click OK, then you just cancel that. Okay. The next step is now to do the analysis. In order to do that, there are 2 options. You can either go here. You will notice now under the analysis, the options are now activated because the data has already been entered, or you can use this option here for a single mode analysis. If you click that, you will be taken to this screen here, then you click OK. Your analysis is complete. What you need to notice here that 2 DN values have been reported. The first one is weighted average DN value that is calculated based on the entire sample, which in this case is 120 millimeter. But there is also a best fit DN value, which is calculated based by excluding the top 15 millimeter and the bottom 15 millimeter of the sample. And this is regarded to be most representative of the sample. The DN values of the weighted average and the best fit, you will notice that they are different. The other observation that can be made here is you will see the black line here represent now the best fit DN value, and the red one is the DN value that is calculated using the entire sample. Then you also notice that the design DN that we selected at the beginning was 6.2 blows per millimeter. So now if you see the green part shows that it is inadequate. That is the case where the DN values are greater than 6.2 millimeter, and that is the yellow part. The green part shows that the design DN values are adequate. That is the case where the determined best fit DN value is less than or equal to 6.2 millimeter. Now let's quickly see how to do a multiple mode analysis. To do that, I'm going to quickly import a data file that has got multiple modes, which is this one here. Once you have imported, you can see here there are about 5 different modes. And in order to do a multiple mode analysis, you have got 2 options. You can either click here on the analysis and then you select multiple mode analysis, or you can use this icon here next to a single mode analysis. It will allow you to do a multiple mode analysis. You can see here there are 2 parts of the screen, the left hand side and the right hand side. The right hand side is where you select the modes which you want to be included in the analysis. You use these arrows here to navigate between which mode should go on the right hand side for the analysis and which mode should still remain on this side of the available modes. So if you click this double, it will take all the modes this side here. Then you can then select the specific modes which you want to use for the analysis, which in this case I will select the first 3. The next thing that you need to note is only the modes that were compacted using the same compactive efforts, in this case intermediate, and conditioned at the same moisture condition can be analyzed at once. So if you try to select another mode that was, for example, compacted using a different compactive effort or conditioned using different moisture condition, if you select that, you will get an error message. It will not allow you to continue with the analysis. So you just close that. Once you have ensured that all the modes have got similar conditions, you click here on the OK. Then again you will see similar results as for the single mode analysis. Now let's quickly explore how to print the analysis report. To do that, you go to File, where you have got an option of either printing a detailed report which is 3 pages document. You can navigate back here, showing the output results as well as the DN data. Or alternatively, you can print a summary report that is only a 1-page document showing a summary of the results. This then concludes the analysis of the laboratory DN test data. Now that you are familiar with the laboratory DN test, we briefly discuss how to record the laboratory test results and how to interpret the laboratory DN test results. It is important that the laboratory work is carried out in an orderly and a systematic manner. Tabulate the test data as demonstrated in this table, including correct sample numbering. The table should include all the test results, including optimal moisture content and maximum dry density of the material. It should also include dry density, relative compaction, actual moisture content, as well as DN test results of each sample. For each combination of compactive effort and moisture condition, a minimum of 3 samples should be tested. The samples should then be used to calculate the average dry density, the average relative compaction, as well as the average best fit DN values. Identify and exclude the outlier results during the calculation of average values. For example, the highlighted third sample for the intermediate compactive effort as demonstrated in this table. From the reported figures, it looks like the sample was compacted at light compactive effort and not intermediate compactive effort. This could be as a result of not working systematically in the laboratory. Therefore, that mode should be excluded from the average calculation. It should be noted that the table illustrates test data for soaked moisture condition only. The test data for optimal moisture content and 75% of optimal moisture content should be tabulated in a similar manner. Let us now briefly discuss how to interpret the laboratory DN test results. Tabulate the average DN test results and the corresponding relative compaction values as demonstrated in this table. On the basis of this table, plot the DN, density, and moisture diagram as demonstrated in this figure. The figure clearly illustrates that for a specific moisture condition, increase in the relative compaction decreases DN values, translating to increase the material strength. It also shows that for a specific relative compaction, as the moisture condition changes from 75% of optimal moisture content to soaked, the DN values increases, translating to reduced material strength. It should be emphasized that the DN values takes into account the grading and plasticity of the material, which are the key interacting variables that affect the strength of the material. Therefore, it is not necessary to specify the grading and plasticity parameters separately. Generally, the greater the separation of the lines in the DN, moisture, and the density diagram, the greater the plasticity of the material. and therefore the greater the sensitivity of the strength of the material to changes in moisture. In a similar manner, the steeper the slope of the lines, the greater the sensitivity of the strength of the material to changes in density, which is a function of particle size distribution. Through comparison with the requirements specified in the DCP-DN design catalog for each pavement layer, the DN, moisture, and density relationship will enable the designer to determine the following. Firstly, whether the material is suitable for use in the pavement. Second, where in the pavement it can be used, based on an assessment of the anticipated long-term moisture condition in the pavement and the field density of the layer after compaction.
By way of summary, the video has provided step-by-step guidance on all the procedures required for assessing the suitability of materials for incorporation in a low-volume road pavement, including the standard procedure for undertaking the laboratory DN test, which is central to the DCP-DN Pavement Design Method. As emphasized in the video, it is crucially important that the laboratory DN test is carried out correctly following the procedure demonstrated in the video. In addition, calibration and checking of laboratory equipment is critical for achieving quality-assured test results. By following the guidance provided in the video, designers should be in a good position to ensure that the outputs of the laboratory DN test are reliable and can be used with confidence as an input to the low-volume road pavement design process as described in the DCP Pavement Design Manual. One of the goals of RECAP is to improve accessibility of the rural poor in Africa and Asia to economic opportunities and social facilities through improvements to road infrastructure and transport services. The attainment of this goal presents a multidimensional challenge that goes well beyond the materials evaluation process described in the video. In this regard, one could say that the successful engineering of a low-volume road requires ingenuity, imagination, and innovation. It entails working with nature and using locally available, non-standard materials and other resources in an optimal and environmentally sustainable manner. It will rely on planning, design, construction, and maintenance techniques that maximize the involvement of local communities and contractors. When properly engineered to an appropriate standard, a low-volume road will provide sustainable access to the rural poor in African and Asian countries through improvements to road infrastructure and transport services. Finally, the production team wishes to acknowledge the support and facilitation provided for the production of this training video by the RECAP Deputy Team Leader and Infrastructure Research Manager, Engineer Nkululeko Letta. The production and narration of the video were undertaken by Mike Pennard, Julius Comber, and Yon Hongwei with the support of CSIR's Road Materials Laboratory staff.